Hello, I'm Anubhav Jain from Denmark Technical University. I'm doing my PhD there as part of InnoDC, which is EU Horizon 2020 program. I'm working on the Blackstart and islanding capabilities of offshore wind power plants. Before I talk about the focus of today's presentation, I'll give you sort of a brief overview of the motivation of my project so that you can have some sort of a context about what the project is all about. A blackout is a very high impact, low probability event, but in the last 20 years there has been an increase in the number of widespread blackouts all around the world. For example, in India in 2012, in the summer, there was a blackout that most of us are very well aware of and went through, and it is by far the largest in history, especially as far as the people affected are concerned. Also in Philippines in 2013, it was the longest blackout by customer billion hours. And in North America, South America, Australia, also continental Europe, there have been significantly large blackouts that have caused chaos, disruption to economy, and affected millions of people. So the motivation for this presentation or for this project is that with increasing integration of renewable energy into the grid, the conventional thermal plants are being phased out, and this has led to an increase in transnational power exchanges. Now, this coupled with power electronics interfaces being more and more present in the system is changing the dynamics of the system and pushing the system towards its stability limit. Additionally, stronger network linking is increasing the risk of wide area blackouts. So large offshore wind power plants, especially offshore, because as you go further from the shore, you have steadier wind conditions and you can build larger wind farms. And moreover, today's modern wind turbines with state-of-the-art electronics control can provide advanced functionalities and thus cater to the Blackstart requirements that typically conventional thermal plants address. Additionally, grid-forming wind turbines, something which I'll talk about in the next presentation, but we can call them, for now, Blackstartable wind turbines. They don't need to wait for network reconstruction to occur, and thus they can facilitate power system restoration much earlier in stages. This can also help, if not totally avoid, but minimize the use of diesel generators that are right now present to supply auxiliaries on offshore substations. And this can, in some way, present some reliability and cost benefits. A traditional power system restoration approach is a combined zonal backbone restoration in most countries, which is basically because you can, in parallel, build regional network islands while also providing supply to auxiliaries of non-Blackstart units, and thus save time, because in Blackstart blackout impact, time is the key indicator of how much impact has occurred. So this is divided into 3 stages: preparation, system energization, and then load restoration. The first stage is essentially the operator assessing the status of the system and then doing a critical planning of the restoration paths and what Blackstart units to use to essentially avoid another occurrence of a blackout. Then Blackstart units, which are being predetermined, are cranked up to power the non-Blackstart units, and regional network islands are formed because priority loads are picked right now, but only to stabilize frequency oscillations, and the high voltage transmission lines are charged for propagating the voltage and getting the transmission system ready. Ultimately, the aim is to pick up loads, so some sort of a block load is picked up, which is determined by the operators depending on the system. It can vary from 10 megawatts to 40 megawatts in larger systems. And this is done while, of course, maintaining voltage and frequency in stable operating ranges. And then for resilience, meshing is done, and finally synchronization between all the islands that are stable is done to ultimately have the complete grid. So a Blackstart service essentially has 3 tasks, which is to start up independently of external supplies, then energize the transmission distribution network, and then provide block loading of the demand. Most of the times it also does provide auxiliary supply to the non-Blackstart power generation modules. It consists of a self-starter, which is typically a diesel or battery energy storage system, and a cranking path, which may be optional if the self-starter is co-located with the main power generating module. That is the generator that takes up the responsibility of ultimately energizing the transmission system and then dealing with the megawatts and megawars of power flow. And each stage has different technical challenges, which I'll be talking very soon. At present, large thermal plants are used to deal with the restoration requirements, and Blackstart units mainly are pump storage, hydro, and gas-fired plants because they can provide big bar absorption capacity and a lot of inertia. In some countries like Denmark and Ireland, HVDC links to Norway and UK respectively are used for a top-to-down restoration procedure. But that's because Energinet, for example, in Denmark has done a study that the probability that they will not have power over the HVDC line during a blackout is very low. Nuclear plants can also facilitate power system restoration. However, right now, especially because they can provide a huge war absorption capacity, but currently, for security reasons, they are only considered critical loads. In the future, since our generation profile is changing with more and more renewable energy coming in and average running hours of conventional synchronous generator machines reducing, it is required that alternate sources also be looked into for Blackstart, for power system restoration, and mainly because this will provide resilience to the system. Large wind power plants, there have been initial studies for large wind power plants to participate in different stages of power system restoration, and there have been some benefits. As far as intermittency is concerned, because if there is no wind, wind farm is essentially almost useless. So energy storage, which this conference had quite some good sessions upon, can provide alleviation to those risks. Now coming to the focus of this paper is, I'm going to talk about very qualitatively without going into details of grid codes and numbers. I'm going to talk about, basically present the main technological requirements for Blackstart units and compare them with the capabilities of wind turbines that exist right now that I've found from different grid codes or studies on ancillary services or literature review. And then we can basically find a gap that exists to make Blackstart or power system restoration through wind reality. The first is, as I talked before, diesel is used for onshore wind is not really a good candidate for power system restoration, mainly because of intermittency issues. However, offshore substations that have diesel generators, an auxiliary and a backup one, can Blackstart and self-sustain themselves. But right now, they are not technologically ready to re-energize the cables and deal with transients in a controlled manner. However, there are innovative solutions, for example, in energy storage at the wind turbine DC link or the point of connection, that can provide some alleviation to risks that might come from intermittency or control problems. More importantly, right now wind turbines are grid following, which means they need a strong or a stable grid connection to connect to. And therefore, if they connect in the initial stages of power system restoration, then that can lead to occurrence of a blackout again. Therefore, this makes grid forming wind turbines, which I think Thomas Ackerman mentioned in one of his talks, but I'll also be talking briefly in detail in my next presentation. Blackstart units are required to have 90% availability so that in case of a blackout, the service can be provided. If stored energy is used, then a minimum volume for 3 sequential blackouts is required, and also a backup fuel for a minimum duration. For example, in case of UK National Grid, it's 3 to 7 days is required from grid codes. In this case, wind is, we don't have control over wind, so when the wind is not blowing, there is no Blackstart service, right? But however, going deeper and deeper into the offshore, having larger and larger, maybe not megawatt scale, but gigawatt scale now, wind plants can assure more steadier wind conditions and thus lesser availability uncertainty. And then, of course, if you have maybe, let's say, 20 Blackstartable wind turbines out of 400, maybe on the edge of the wind plant, that can provide some extra reliability or cost benefits and help also save the insurance costs for diesel, for example. As far as startup time is concerned, wind turbines are really fast in ramping up, given they have the auxiliary supply or a battery storage. For example, GE has an internal battery now in one of its wind turbines. But one important thing is that Blackstart units are required to maintain operation for at least 24 hours after having started, but this is not applicable for pump storage hydro, because you would not want to exhaust the water in the, I think it's called the upper forebay, because you want to have, if another blackout occurs, you need to have another service possible. So some sort of similar relaxation in grid codes, which TSO is, at least some in Europe that I met, they can provide some sort of a relaxation. For example, instead of 24 hours, they could allow only 8 hours of operation as a minimum requirement. But what's important is to use this large amount of power from the wind in the initial stages of the restoration procedure. As far as system energization is concerned, Blackstart unit is required to absorb the megawatts, the capacitive reactive power that is generated by the connection of low-loaded lines and cables. Wind turbines, due to their state-of-art power electronics interface, can provide quite fast wire control, and also very new grid codes are showing voltage right through and reactive current injection requirements. So there is very good capability matching here. As far as the energization sequence is concerned, a soft sequence is preferred to a sequential one, mainly because building up the transmission network in parallel to the Blackstart unit startup at a low voltage helps save a lot of time. And this also helps deal with transformer inrush currents, especially on the low voltage, the medium voltage transformers, and also maybe mitigate the resonance that can happen between long high voltage lines which are connected to unloaded transformers. Wind turbines with their type 4 wind turbines with their state-of-the-art power electronics control can provide very fast reactive power control, and now especially in the grid codes of Germany and Spain, local voltage control requirements are expected in the future, if not already there. For frequency control, load pickup is used during restoration process, as I mentioned earlier, and it is the priority loads that are picked up first in small steps, with a minimum requirement that frequency be a bit over 50 hertz, so that when the load is picked up, it doesn't go to another frequency instability point. However, upward reserve is very important during the initial stages of the power system restoration to deal with fluctuations in the offtake of reconnecting grid users. And different numbers are there from different transmission system operators based on their network capacities. Wind turbines, again, because of their power electronics control, can provide very fast ramp up of real power. But the reserve exists more in the down-regulating zone. However, with energy storage, this can maybe even be more beneficial. Fast frequency response by using kinetic energy of the rotating machine can provide some sort of a stabilization to the initial drop of frequency. However, this is not really power system restoration, but some inertia emulation and power oscillation damping, which is expected again in the future grid codes of Spain and Germany, are quite promising features. Ultimately, picking up block load, which for example in Ilia in Belgium is 10 megawatts, for UK it's about 40 megawatts. This is for a 400 megawatt farm with maybe good or almost rated power production. This is not really a big deal. However, what's important is to maintain stability of operation and thus controlling the voltage and frequency within stable operating range. And for this, some sort of a curtailment is required. Some grid forming capabilities are essential. That I'll also talk about in the next presentation and show some initial results. Right now, islanding or trip to household feature of power PGMs is not really used in power system restoration, although it's very good because then it saves time to not really ramp up the PGM from start. Except in France, I think they use some TTH operation. TenneT has grid codes regarding the connection of PGMs to be able to switch to TTH from any operating point, and large 1000 megawatt PGMs to have islanding capabilities. So if offshore wind power plants can do a control being very important, islanded operation of the offshore island, it can help save a lot of time in the power system restoration initial stages. Summarizing, the main important requirement is grid forming or Blackstartable wind turbines, because this can help build the local voltage and frequency and the collector grid, and also power up or energize the auxiliaries and the cables. Right now, offshore wind turbines, the large ones, can deal with the megawatts of array cables. However, the export cable energization is a bit far from technological readiness. And then ultimately dealing with transients in a controlled manner, especially the large transformer inrush currents, resonance issues in the HVDC link needs to be studied, and a controlled islanded operation has to be guaranteed before a wind farm can provide a power system restoration service to the onshore operator. A brief overview of the different target states of a possible a Blackstart energization sequence. The different technical challenges and control solutions have been presented in this paper that was submitted in the wind integration workshop last year. So if you need, I can send you on ResearchGate or any other media. I won't show the results right now because I'm going to be talking about it in the next presentation. And some important points. Currently, the grid codes of mainly countries that have more experience dealing with large wind penetration, offshore maybe penetration, do provide technical requirements of connection of wind turbines at the HV and the EHV level for PQ control, voltage support, inertial response, protection, and fault right through. However, there is exemption from power system restoration services. Now, grid codes have been a major driver for wind turbine technology in the past. For example, recently, reactive current injection and inertia and power oscillation damping is quite a good example. And therefore, an ongoing dialogue between the wind industry and the transmission system operator is very essential to make this a reality. One really nice case study that the Australian operator presented on the 2016 South Australian blackout in Cork at the WESC conference, the Wind Energy Science Conference, just this year in summer, was about how redesigning or just the changing protection settings of the wind farm, especially in areas of high wind penetration, could have prevented tripping, unnecessary tripping of the large wind farm, and saved the system from splitting and leading to a blackout ultimately. And also, they do suggest more practical measures to be implemented for stable islanded operation. And they have done simulations that show that wind intermittency and excessive speeds are not really a material contributor to blackouts. But, however, further investigation is required because modeling the impact of wind on the power system resilience is quite a challenging task. And I mean, you can clearly see it took them maybe 2 years to get some sort of a initial study done. Last but not the least, it's important to mention that Blackstart units are used to kick off the power system restoration process from a completely dead state. So their impact is very important in the first 4 to 6 hours of power system restoration. And later on, there are many other factors that can create problems. But however, it's maybe more easier for countries like Denmark, or Germany and Spain, Ireland maybe, who have more experience dealing with larger wind energy penetration levels, to maybe look into this or can deal with these problems on a much more experienced manner. With this, I'd like to thank you all for your attention, and I'll present the second.
Can you skip the time to 15 minutes? We have a
okay.
Till 11 o'clock we have to finish.
Okay, perfect.
So try to finish with 15 minutes.
Okay, thanks. So this presentation was from Dr. Jayachandra Sakamuri, who is now in Vattenfall and therefore could not come. And it's about, it's a bit different from what's mentioned in the scheduled agenda. It's on Blackstart and self-energization of HVDC connected offshore wind power plants. This is the agenda. I'll be just briefly mentioning why HVDC is required and what's the need for self-energization. And then I'll be talking briefly about grid forming capabilities, and then showing you some initial results of such a Blackstart capability of offshore wind power plants. So, since to avail the wind energy farther from the shore, offshore wind plants are going deeper and deeper, farther and farther away from the load centers, and longer AC cables become at some point inefficient to transfer real power because of requirement of reactive power. Therefore, DC cables are the way to go forward around maybe after 80 kilometers or 100 kilometers. And this also presents an additional benefit that it decouples the offshore wind power plant from the onshore grid, and thus makes it sort of safe. Currently, the offshore AC network is energized from the onshore side by utilizing the grid forming capabilities of the offshore HVDC converter. Thus, in case of an outage in the onshore side, auxiliary power supply, which is mostly diesel generators, sometimes batteries are used at the offshore platforms to power up the auxiliaries and then get the wind turbines running. However, modern Type 4 wind turbines, which have fully rated powertronic systems and hope in the future grid forming capabilities, can energize the offshore collector grid, maybe, and also power up the auxiliaries, deal with the charging requirements of the cables, and then charge the converters, the HVDC link, and finally provide power system restoration services. So this is, for example, one grid forming control. I will not go into the technical details, but it essentially, instead of controlling this converter, the voltage source converter as a current source, you control it as a voltage source with a voltage and frequency reference. There exist different grid forming controls, and it is just a control matter. There is no special change that is required on the converter end. This is the system that I'll be showing the initial studies results about. It has a wind plant with some sort of an aggregation, and then the offshore transformer with a PIR to deal with inrush transients, detailed MMC models, and a HVDC cable link of about 400 kilometers, and then the passive load. But this is just an example system. Of course, a more realistic scenario can be used. However, this was just to see if it is possible to Blackstart the onshore side by wind turbines. So the sequence is as so that the wind power plant starts grid forming the offshore collector grid, then the main breaker is closed, and then after some delay the PIR is bypassed to deal with the transformer inrush. And then at 2.1 seconds the offshore MMC is deblocked, ultimately controlling the HVDC link. Once that is done, the onshore MMC is deblocked, and then that controls the onshore grid, and then the passive onshore load is picked up. These are the initial results. You can see that the PIR helps control the charging of the inrush currents, and the offshore converter submodules, there is a transient, but then when the submodules capacitors are charged, the HVDC link is controlled. During the onshore converter being deblocked, there are, as you can see, very considerable oscillations in the voltages of the submodule capacitors of the onshore converter and the onshore converter. This is because the offshore MMC capacitor, submodule capacitor energy is used to energize the onshore MMC submodule capacitors, and this can be done in a controlled way. However, right now there is just uncontrolled, but ultimately it does reach steady state, and then the onshore voltage is starts to be formed. At 4 seconds we pick up an example passive load, and there is an HVDC link voltage drop, but once the wind power plant power starts supplying, reaching the onshore side, the transient disappears. So in conclusion, with grid forming capabilities, wind turbines can be used to energize form the offshore collector island, energize the HVDC link, and ultimately provide block load picking up capability. PIRs or synchroscopes point of wave switching can be used to deal with inrush transients of large transformers, and this is a very initial study in showing that in the future, large offshore wind power plants can provide power system restoration to the onshore grid. Yeah, thank you so much for all your attention, and if there are any questions that I can address, I'll be happy to help.